let's do some introductions here. My name is Ioannis Glaropoulos. I'm a software engineer with Nordic Semiconductor. A little bit of more introduction for you. I'm happy to be invited by the Technical Steering Committee to give a talk in this conference. Actually, it's a very nice conference, a lot of nice Linux presentations. And actually, I really enjoy presentations and the interactions with the audience, questions from the audience. But this is not a Linux talk, this is a Zephyr talk. So I hope you find the topic interesting. I hope you also ask questions. Just like off the record, how many of you have heard about the Zephyr operating system? Please raise your hands. Okay. Almost everybody in this room. Okay, that's good. So that's going to be fun. That's going to be interesting. I will say a few things about Zephyr because I actually don't have a slide for that. So Zephyr is an operating system, a modern operating system, real-time operating system targeting low-power, low-end devices, basically for Internet of Things, for connectivity, but for other things. It's hosted by the Linux Foundation, so this is a Linux project. It has momentum at the moment. It actually has good publicity. A lot of companies joining, backed by big companies like Nordic Semiconductor, smaller companies like Intel or Texas, or maybe the other way around. Yeah, sure. So, yeah, of course. And lots of boards, lots of platforms, more than 350 contributors at the time, more than like 50 maintainers. Myself, I am as a Nordic semiconductor engineer, I'm actually working on Zephyr. I am in the technical steering committee of the project, and I'm also the contributor and the maintainer of the ARMv8 support in Zephyr, so the support for the modern ARM last version of architecture for microcontrollers, Cortex-M23 and Cortex-M33. Yeah, so that's about the introduction. Let's move to the agenda of the presentation. So the presentation is about trust execution in Zephyr operating system. It's about our contribution in Zephyr. So I'm going to guide you through some background, some preliminaries in the beginning. I'm going to talk about why security is important in embedded devices nowadays. And then I'm going to walk you around the concepts behind trust execution and TrustZone, which is the ARM version of doing trust executions in Cortex-M microcontrollers. And then I will move to the presentation of our contributions in Zephyr, basically the trust and execution APIs, and also a solution of how to build applications in Zephyr OS with trusted firmware. And then I will conclude this talk with some discussions about our future plans and directions. So a couple of slides about Nordic, not really too much, just to show you who we are and what we do. So we're a company strongly positioned in solutions for wireless connectivity, for basically internet-connected things. We focus on Bluetooth, but we do have other technologies, of course, supported. We have 15.4 based technologies like Thread, Zigbee, and we also recently launched our latest and greatest SoC with support for narrowband IoT, cellular LTE. We see ourselves as an IoT enabler, so we are happy to see our SoCs, our silicon, embedded in all products within the whole spectrum of Internet of Things use cases. So what we do sell to the customer is the SoCs, the system on chip solutions, the silicon, but we do provide also a software. We implement our own protocol stacks for connectivity like Bluetooth, Bluetooth Mesh. We also provide SDKs, a bunch of drivers for our SoCs, solutions and examples how to use our protocol stacks. We also give out some front-end applications and of course, development kits like this one for companies to prototype their solution. I can show you more development kits later after the recording is over. So let's move to the presentation, to the main topic of the presentation, trust execution and security in embedded devices. So please ask me any questions you want during the presentations. If you don't understand anything, just feel free to interrupt me. So that's a slide where I would like to argue why security in embedded devices is a really important concern. So I heard yesterday that we live in 2018. Yes, that's right. And so in 2018, embedded devices are not tiny. They are typically strong processors with clocks around 100 megahertz, with lots of kilobytes, hundreds of kilobytes of flash and RAM, lots of interfaces, radios, sensors. So those devices, they are expected to run, and they do run complex software. And what's maybe different from embedded devices in the past decades is that the embedded devices today, they are connected and they are remotely accessible. So they are connected to the internet, accessible from the internet, and they are also connected to and from each other, for example, forming complex topologies like in a Bluetooth mesh. So it's very important that all this communication with embedded devices happens in a secure way. Secure protocols running on embedded devices, they provide secure services, perhaps to authorized entities and authenticated parties. So they need to run in a secure way, and they do use sensitive information like passwords, keys, secrets. And all of this, it's very important from the security perspective that untrusted software and untrusted entities don't have access to this sensitive data stored on the devices. Embedded devices today are also part of large systems, and sometimes very large systems, like think about, for example, a smart lighting installation in an industrial building with hundreds of nodes, or even sometimes thousands of nodes on one network. So security is an important concern because even if you can manage to compromise a couple of devices in this network, there is a high risk that the whole network or the whole system is compromised. Embedded software, besides embedded devices, is also complex. It may be buggy, just because IT companies, they rush to release software. They release bugs sometimes, trying to gain market advantage by doing early releases. So most of the times, embedded software, it's buggy. It requires frequent updates, frequent remote updates. It needs to be updated multiple times. And it's very important that this whole thing is done in a secure way, so the devices are still functional and operating after a firmware upgrade. But my favorite argument for security in embedded devices is that the fact that modern embedded devices, they contain software that is usually developed by multiple entities. Okay, so when you get an IoT product, an embedded device, usually the silicon vendor might have written some piece of software, let's say initialization software. Then it's going to be the platform maker that has probably contributed there the main system software, drivers, peripherals, perhaps an RTOS, or protocol stacks, and so on. And at the end of the day, there is the application, the product maker that has written the application software. Okay, so all these parties, they write software for the embedded devices that you see, and they all of these software parts run together. But in principle, in theory, all these parties should not trust each other. Okay, so and it's very important that at least the critical operations running, executing on the embedded devices are protected in a way that the device cannot be compromised by malicious or accidental bad software written by an application, for example. So here is just to illustrate this a little bit more and visualize it. I thought about the most simple example of IoT use case, right? An SoC having a sensor over SPI or anything else, and just having a connection to the cloud service over TLS, MQTT, and just read the sensor reading every now and then and just transmit it to the cloud service. Okay, so that's the most simple example I thought about when it comes to IoT. And then this is only to visualize what types of threats we might have. So this SoC has a bootloader, perhaps, some initialization code, stores some sensitive data to talk to the cloud service, has some system software and application software. So what can go wrong in this device? Well, a lot of things, as I list here, and maybe things that I actually forgot to say. So secrets for embedded TLS or MQTT can be exposed to unauthorized entities. Yes, that's a big threat. Bootloader can be corrupted. So root of trust establishment in the device can be corrupted during device boot. It may make the bootloader to load unauthorized, unsigned application firmware images. Sensor data coming from the temperature sensor can be exposed to untrusted entities, untrusted software running on the device as well. That's also a big threat. You don't want to do that. Unauthorized access to device managers, system logs by application software. Yes, application software should not have access to device management. So all these things may happen. There are examples of threats in embedded devices. And this leads to reveal the need of having a trust execution environment in embedded. So what is a trust execution environment? A trust execution environment is basically a secure area inside a CPU, inside the microcontroller, where the code that is executing in this area, the instructions themselves, the code, the data it generates, and the processor state machine, so the processor state during the secure execution is all protected and hidden, obscured by the untrusted software, non-secure software executing also the embedded device. So basically, trust execution tries to address four big things: data protection, firmware protection, operational protection, and communication protection. So data protection is important so as to avoid sensitive data, keys and secrets and passwords to be revealed to unauthorized access. Firmware protection is also important. For example, you would like to have read-back or write-back protection on sensitive parts of the system like bootloaders, so just not to bypass root of trust. Operational protection is important, so critical and trusted functionality should be run uncompromised in the device. And communication protection is also important, like you don't want, when you execute protocol stacks, data that's generated to be exposed to untrusted parties. So let's move now to TrustZone, which is the ARM way of doing trust execution in Cortex-M microprocessors. So TrustZone realizes trust execution by defining two processor states, two execution states, the secure state and the non-secure state. So the secure state is the trust execution environment. When code executes in the secure state, basically the code has access to pretty much all CPU resources, like flash, RAM, areas, peripherals, CPU state. While code that executes in the non-secure state, in the untrusted part of the execution, usually it has only limited access to a certain amount of resources of the system, usually marked, or to use the TrustZone terminology, resources attributed as non-secure. In order to address data protection and communication protection, TrustZone enforces hardware-based isolation between the secure side and the non-secure execution environment. And this isolation is enforced by TrustZone actually defining one and only one way in which execution can transit between secure and non-secure. So TrustZone defines non-secure function calls, which is the way to move from secure to non-secure execution. And usually non-secure function calls are accompanied by stacking all secure context and clearing it before jumping to the non-secure execution environment, so this content is not leaked to the non-secure code. Also, TrustZone defines the opposite, so transition from non-secure to secure execution through non-secure callable entry functions. And this is totally configurable for the developer, for the secure developer, how big will be this API, this surface attack. So how big will be this group of callable entry functions that can make non-secure code to transit to secure execution. And of course, TrustZone also, in order to catch and to detect and report violations of this transition scheme, it introduces a security fault mechanism. In order to address now operational protection, TrustZone defines the concept of resource banking. So pretty much everything on your CPU, on your microcontroller, like stacks, stack pointer registers, MCU control blocks like memory protection units, floating pointing units, interrupt vectors, faults, control registers, pretty much is banked between. So they have double instances, secure instances and non-secure instances. And this actually allows basically to visualize TrustZone as two independent processors running at the same time, the secure execution and non-secure execution, and just simply perhaps sharing the program counter. Okay, that's pretty much nice about TrustZone. So to go a little bit more in depth about TrustZone, allow me to say that the concept of secure and non-secure execution is orthogonal to other well-known concepts in embedded programming like thread and handler mode for processors, or privileged or unprivileged execution. And so for example, we have like a secure thread mode and non-secure thread mode, secure privileged execution and non-secure privileged execution. The top figure on this slide shows exactly how the branching can happen from secure state to non-secure state. And usually what is nice about TrustZone here is that when you branch by calling a non-secure function call from secure state to the non-secure state, usually it's the responsibility of the compiler and the hardware to do all this seamless prevention of secure content leaking. So all this context stacking and clearing happen automatically in a magic way, and then that's very nice for the secure code developer that it doesn't have to literally do these things by himself on the C code. Pretty much everything on the MCU with a TrustZone can be configured as secure or non-secure. So faults can be configured as secure or non-secure. Exceptions, system exceptions, hardware interrupts can be routed to the secure or to the non-secure execution context. And pretty much everything else, like flash or RAM, memory areas, ranges, kernel objects, or anything, can be attributed as secure or non-secure with the dedicated IP security attribution unit that you have on TrustZone computers. And of course, TrustZone comes with a secure fault and the corresponding secure halt fault that detects and reports security violation. So just to complete this tutorial about TrustZone, where is all this thing needed? Where is it used? So like I said before, TrustZone is there, and trust execution is there in order to obscure critical trusted operations and sensitive data from unsecure code. So in the terminology of TrustZone, all these critical operations are called secure services. So what I list here in the figure below is the basic secure services, the most common secure services that I can think about. So crypto services, secure storage, secure boot, key management, secure attestation. So all of them correspond, or all of them comprise the secure execution environment of an MCU. And then the secure entry API, so the secure entry functions, is the way for the system software on the embedded device, the RTOS, and the applications, how they can use the secure services. So questions so far about TrustZone. Any questions you would like to ask? Is everything clear? Good, that's nice. So I gave you the tutorial about TrustZone, so let's look now about let's look on our contributions here. So in Nordic Semiconductor, this was a project that we started maybe a bit more than 6 months ago. And say, let's bring TrustZone support in the Zephyr operating system. So Nordic is experimenting with Zephyr. We believe in the future of Zephyr. We invest because we believe in that, and we have primarily contributed a lot of other software components to Zephyr, so that's not the first thing. What made this contribution a little bit special is because the whole thing is new. TrustZone and trust execution is new when it comes to microcontrollers. So basically, we didn't even know what kind of APIs we should implement actually there to have TrustZone support. And to make things a little bit more hard, we didn't even have a reference implementation elsewhere of TrustZone to see what kind of implementation we need to have. So that was the bad news. But then, of course, when you realize this case, you say, all right, I'm going to start on this kind of bottom-top approach. So I have nothing in my hands, but I do have the TrustZone specification from ARM. So we're going to begin with bringing in, step-by-step, the core TrustZone functionality and ARM v8m functionality in Zephyr. So that's what we did. That was the first thing that we addressed in this project. And then when everything was there, sorted out, next question was like, OK, what do we do now? What do? We have TrustZone in Zephyr. So we want to build Zephyr applications with trust execution. And then we have to answer questions like how to integrate everything with the Zephyr build system and configuration system, like things like kconfig and device trees. And basically how to organize our device firmware to support trust execution. So that was the second thing that we did. And then last thing that, of course, troubled us is like Zephyr, it's not an ARM-only operating system, right? It's a cross-architecture. So at the end, what we would need to have here is generic APIs for trust execution, not ARM-only. So let's start step by step, going through our contributions here. So like I said, we have ARM-only APIs for TrustZone in Zephyr. So we have created APIs and implemented them, allowing the secure developer, secure user, secure software to configure security attributions of memory areas like flash, RAM, kernel objects, semaphores, or whatever, put them in secure or non-secure side. We have made APIs allowing the user to, at runtime, when the software runs, evaluate the security configuration of certain areas. We have created APIs for managing interrupts, faults, exceptions of the system, routing them to the secure or to the non-secure world. And of course, we have made it easy for user to use the TrustZone APIs to transit between secure and non-secure execution. So we created new function pointer types to simulate non-secure function calls and secure entry functions. So the two ways you can just bounce between secure and non-secure execution. We implemented secure fault handling in ARM with deep inspection of all stack context upon secure faults, and we integrated that into the Zephyr fault handling mechanism. And of course, we integrated the whole TrustZone into the Zephyr build system, meaning that we created kconfig variables to denote trust execution compilation. We translated this into CMake in order to have GCC compilation options for enabling TrustZone. We wrote some scripting on the linker side, creating and manipulating, for example, sections to put secure entry functions, dedicated sections for secure entries, and export symbol tables and libraries for the secure entry APIs. So after doing all this, then yes, of course, we wanted to build applications with trust execution in Zephyr. And the proposal we made, quite intuitive, was like, OK, if someone wants to build an application for a TrustZone-enabled microcontroller, in Zephyr. Then he will have to build his secure firmware part, and then he will have to build his non-secure firmware part, and finally combine the 2 or the 3 different firmware parts to create the entire device firmware. So, and then it's a question of course, what software components go into the different parts. So most likely the intuitive approach here is that full RTOS drivers applications go to the non-secure side. The secure side implements the secure services that I spoke about before, like secure boot, secure storage, crypto operations, and so on. So we realized that when you want to do this framework for device firmware, you basically have 3 types of firmware that you would like to implement. So the yellow part is the so-called secure non-aware images, secure non-aware firmware. So images that actually ignore TrustZone. So firmware images that just ignore the presence of TrustZone in your CPU. So they will never transit to non-secure code execution. And for that reason also they don't need to implement secure fault handling. So typically these images, these firmware parts will be the first stage bootloader, the first piece of software that runs when you boot up your embedded device. Then of course we have the secure aware images, the images that they do implement TrustZone. They implement all the secure services I spoke about before. So they run all the secure libraries. They should have a way to configure security attribution, so use the APIs that we created before. And then, of course, they should allow transition to the non-secure side. And for that, they need to implement secure fault handling. And finally, we have the non-secure aware images, the green ones here that they basically run the kernel, everything else. They should be aware, this kind of images, they should be aware that they do run in non-secure mode of a TrustZone-enabled microprocessor. So they should be aware that they shall not directly access secure MCU resources. Otherwise, they could create faults. And of course, they could only access secure execution through the secure entries APIs. So this is the way we have 3 types of firmware. Of course, 2 variables is enough to represent all those categories. So trust execution secure and trust execution non-secure are the only 2 kconfig variables you need to build secure and non-secure firmware in Zephyr. So here is more or less how an example of a device firmware could look like. So the non-secure firmware at the bottom of the line will contain initialization code. The secure non-aware firmware in the bottom, the yellow part, will contain initialization code, perhaps implementing root of trust, modules for device firmware upgrade, and maybe store device boot keys. So this firmware shall not really care about TrustZone at all. It's going to be the hidden first stage bootloader. But then eventually this firmware should load the blue part, the secure aware firmware, which can be the bootloader stage 1, so the second stage bootloader or any other piece of secure firmware manager. And that should contain the security manager of the system, should implement the secure services I spoke about before. It needs to have some area where to store secure data, right? Sensitive data that cannot be exposed to non-secure execution. And then maybe also have some modules, some secure device drivers if some peripheral, some hardware of your system is supposed to only execute in secure state. Finally, the secure aware firmware or the bootloader 1 should allow the real application to execute in your device. So your RTOS and your application containing the Zephyr kernel, protocol stacks, device drivers, pretty much everything else. Yes, so the last challenge in this kind of firmware organization is how to actually how to address the problem of security aware boot time configuration in Zephyr. So let me give you actually first the background why this was needed. This was needed because of this peculiarity of TrustZone microprocessors. So in microprocessors of ARM with TrustZone, basically, depending on whether you access a resource, a peripheral address space, or an MCU control block, whether you access it from the secure execution state or the non-secure execution state, then the address map may change. So we basically need different hardware descriptions. So to give you a quick example, you might have, for example, a UART peripheral, right? And then you want to configure the baud rate of this UART peripheral. And then most likely this is like a register accessing your peripheral address space. So the register, the value of this register will be different, whether you access it from the secure or the non-secure side. So what you need at boot time, at build time of your firmware, is to have different hardware descriptions for the secure and the non-secure domain. So allow me to say that this challenge was maybe not trivial, but not really a hard one. we utilized the Zephyr device tree for this reason. So basically, we solved this, we addressed this problem by having separate device tree source descriptor files to describe hardware that to be used by firmware in the secure side and firmware in the non-secure side. So DTS descriptor files for hardware description, boot time configuration, image planning, and overlay DTS files, they were all duplicated in our build system for the secure and non-secure side. And the figure here shows that depending on whether the kconfig options for secure execution or non-secure execution was enabled, the different DTS files were put into the DTC compilation. And in the end of the day, everything was automated smoothly. So we were able to get our auto-generated device headers for hardware description to put into software compilation. Yeah, so that's pretty much all I wanted to say about what we did for TrustZone, for trust execution in Zephyr. And allow me to spend the last couple of minutes of this presentation presenting a little bit of our future plans and directions. Yeah, we recognize that Zephyr is a cross-architecture RTOS. We like that this is not an ARM-only RTOS. So eventually, what we have to do is to move all the work that we did, all the API definitions for ARM, to move it in and to generalize them in Zephyr, right? To make this application, these APIs for trust execution generic, so they can be used eventually by any architecture that supports trust execution. And what will be a little bit tricky in this case is how to do secure peripheral management in Zephyr. And the reason that this will be tricky is the fact that still Zephyr doesn't have a uniform way of addressing peripheral management at the point with driver and hardware management. Future plans number 2. So we would like to see some of the most common basic secure services, secure applications natively supported in Zephyr. To name a few, we would like to see secure boot, root of trust implementation establishment and key management, and perhaps secure peripheral services to be natively supported in the Zephyr OS, in the Zephyr tree. And we would like to come up with the design and the reference implementations. But of course, we don't want to do everything in Zephyr. I mean, sometimes it's use case dependent what kind of secure services you need to have. So eventually, what we want to provide is generic APIs in Zephyr to allow people to build their own secure services in Zephyr or outside Zephyr. So the point here is that to be able to offer, to export a generic secure service API in Zephyr for trust execution, so some people can use other open source projects to implement their own secure services and then plug them to Zephyr to create builds for applications that support trust execution. So that's all I had to say. Time for questions. I'm happy to answer questions now and, of course, outside. Couple of links for you. If you want to know more things about ARM TrustZone, here's a link to ARM documentation. If you want to know more things about Zephyr project, that's a link to the project website. And if you would like to see the progress and to also collaborate on trust execution for Zephyr, I'm just giving here the link to our GitHub project. Thanks for your attention.
Thank you. The first question.
Thank you for your slides. I have at least 2 questions. First of all, as I understood, you want to use trusted execution experience, extend trusted execution experience on the desktop processors and desktops and servers at all. Yes?
Embedded devices, basically.
Only embedded devices.
Yeah.
Only embedded device. You said this, that your model based on 2 parallel working processors. Yes, but you said almost nothing about how you implement your trusted execution at all. Or maybe I don't understood.
Yeah. So allow me to clarify this. So trust execution is implemented basically on hardware. So it's something that ARM has implemented. It's the TrustZone model of isolating between secure and non-secure execution. And what we implemented is a support on the API level. So the high-level support inside kernel code. So for the user that wants to write secure software, to have an API to actually dictate the secure execution to move between secure and non-secure state. But itself, the trust zone is a hardware implementation. Okay, so it's a little bit below the level of embedded software design.
Okay. Just one more question. If I have some service, can I wrap it into secure service and run as a secure service in the secure space?
Mm-hmm. That's right.
How can I do it?
Yeah. So you have to. So assuming that this service is some piece of code that you can compile into a Zephyr application, all you have to do is to compile it with all the other components that you want to run on the secure side. So basically, this application that you said implements some secure service, this piece of code, this piece of software, this piece of library, together with all the other necessary parts of the secure execution, like security manager, secure data, needs to compile as a blob, as one thing, and then you will create a secure part of your device firmware. And then you have to compile, of course, the counterpart, the non-secure part of the firmware, merge them together, and this will give you the whole device firmware in the end.
And if I need to use a secure device driver or secure data, I should get outside of secure space into user space or something else, or I can interpret directly in secure space.
Yeah, so the idea here, that's actually a good question. Maybe I should have clarified that in a better way. Of course, this secure data that you see here on the blue part on the secure side are useful data, right? They are needed for executing critical operations in your MCU. So maybe the green part of the software that you see, the Zephyr kernel or the applications actually need access to those data. But the whole point about trust execution is that we put this data on the blue side, on the secure side, we protect them. And if anybody from the green side, of the non-secure side, wants to access the data, they have to do it through the secure services. So it's not that we're hiding this data forever. We're not hiding this information, this content from the non-secure world, from your applications. We want, but TrustZone is the way that we want to expose it on a way that we are sure, or at least we are almost sure, that they will not going to be exposed to malicious software or accidentally to software that should not have access to it. So they should go through a predefined way through the secure service that should actually authenticate the request from the non-secure side to access the data. And if the request is approved, then the data can be accessed and can be exposed to the non-secure side. But TrustZone is all about controlling the way that this is done.
Okay, thanks, Ioannis. Great talk.
Thank you.
Love to hear that. Functional safety and TrustZone. So say I want to have a device that would run in a hospital. Probably I need to certify that, right?
Mm-hmm.
Do you believe that this TrustZone would make it easier or would not affect the safety certification?
Yeah, so TrustZone is the hardware IP, is the hardware solution provided by ARM. But of course, ARM has come up also with the platform security architecture behind that. Meaning that ARM promises to an architecture, a hardware architecture that achieves trust execution and will work on the field. But he has promised also a lot of specifications how this architecture needs to be actually used in embedded devices, and also promised that there will be an entity that will actually certify that your device is, so to say, trusted execution compatible. And this will be, I guess, the umbrella framework under which devices can claim that they are secure and they can be used in areas like you mentioned, like functional safety. So alone, trust execution doesn't do much if it doesn't come with a high-level certification or high-level actually specification of platform security architecture for embedded devices. But it will come, and then also, of course, the next step is certification authorities that will actually verify that your devices will operate as they have to.
Thank you. One more question?
Yeah.
Hello, thank you for the presentation. two questions actually, and just trying to get a sense. I may have missed that point. Just trying to get a sense of what would be the case when we switch from secure to non-secure mode or whatever it's called. It could be possible to do it kind of online, right? As I understood.
Kind of
online, like on the fly.
Yeah.
So what would be the case for that switch? That's the first question. Like, why we need to switch from secure to non-secure?
Yeah. So, if I understood the question, and the obvious answer is that if you believe that this is a kind of like a practical example, so at device boot, will be on your yellow part of the firmware. Then you switch to the blue part of the firmware, the secure aware firmware bootloader 1. And this is like a one-time switch, right, as you see here on the arrow. But then you may have to switch back. You will eventually have to switch back to start executing non-secure code, because it is there where most of your firmware lies. It is on the non-secure side. So eventually, after some initial bootloader work here on the blue part, you will switch. You will implement this non-secure function call to start running your application, start running your kernel. And then periodically, or sometimes not periodically, asynchronously, interruptly driven or whatever, maybe things happen on your green side that require some kind of like secure operations to be completed. So at some point, maybe you want to establish a TLS connection to some remote service when you're running your green applications. And for that, you need to have a key. You need to have a password or something like sensitive data. Then you will switch back to the secure side, request that data, get that data, and then establish your channel. So it is expected that during the lifetime of your device, of your embedded device, when it runs, to switch often between the secure and non-secure side.
Okay, and one more question. When we have two hardware, the one is running secure firmware and another one non-secure, is there any performance degradations in general between those two, or it's kind of they run the same, pretty much the same from the performance standpoint?
Okay, that's actually a very good question, or at least actually gives me the opportunity to say a few things here. So all of this in a TrustZone computer, in a TrustZone microcontroller, all of this is like in one CPU, right? Of course, there are also, this allows me to say that ARM has also a trust execution solution with a dual core machine. So a Cortex M0 running the secure side and Cortex M4 running the non-secure side, okay? But this is not the case what I explained here. This is the case about everything running on the same CPU on a Cortex M33 CPU with a TrustZone. However, what is, so in the end of the day, it's like one processor. So there is nothing about like seeing performance issues and comparing the performance on the secure and the non-secure side. But what is actually important here to mention, perhaps, is that the secure side and the transitions between secure and non-secure executions, they do have overhead on your system. So you do see overall the performance degradation if you have to bounce too often between the two sides. And this is actually important when you will, I mean, this actually plays a role and has an impact on your decision what kind of software components you will put on your blue and your green areas. What kind of software, so you need to make build time decisions, what kind of software should be done, should be put on the secure side and non-secure side. Not always decision based on what kind of security requirements you have, but also sometimes performance requirement. If you put too many things on the secure side, and then you have too many bounces during the lifetime of the device between secure and non-secure side, yes, you might experience like performance degradation that is not acceptable for your use case. So then you have to be actually very careful.
Okay. Thank you. We have time for, okay,
yeah,
we have time for two questions, okay.
Do you consider certain vulnerabilities against such devices?
Yeah, that's actually a good question. I'm not myself the architect of TrustZone, so I can actually speak freely here. The model claims that it works, and actually it works. It does what it means to do. So when you run on the secure side, you must do something very bad in order to expose things on the non-secure world. But still, the code that runs here on the blue part, it's still code written by developers. So in the end, it's the responsibility of the developer not to expose any holes to the non-secure side when they're executing on the blue side. So the general idea behind actually alleviating the risk of vulnerabilities is to write as little as possible of a device firmware on the secure side, and of course having your secure code under much higher scrutiny level when it comes to releasing production firmware.
Thank you. The last one.
I have a small question about devices. I see device drivers in the secure side and on the non-secure side. So as I understand, we can access some device from the non-secure side. So if, for example, secure and not secure code try to access one device, can I implement some catch to preventing non-secure code to access device? Because, for example, if I want to show some information for user and non-secure code can interrupt me and show fake message, for example, how can I protect from this case? Thank you.
That's also a very nice question. Thank you. That's a candidate for a good question here. So it's really many questions. I would have a problem to decide. So what I have in mind when I discussed this example as a possible example of firmware organization is that we do this kind of static planning. So when you have a device that you think or you believe or by design it needs to be accessed only by secure code, let's say some kind of crypto accelerator, then you put it on the secure side, but then it's statically allocated on the secure side. So most of the cases, in most of the common examples, allow me to say on the 99% of use cases, it's not going to be the same peripherals, the same hardware, and the same device drivers that need to be accessed at the same time between the secure and the non-secure side. So this is more like of a static, of a build time configuration of your system. Now, just to answer a little bit more on your question, yes, it's possible at some point that you need to do runtime configuration of a peripheral to be allocated to the secure side or to the non-secure side. So the vulnerability actually here is that you need to be aware that when you are moving a peripheral from the secure to non-secure side, you are also clearing this peripheral. You are also resetting this peripheral completely, so no previous information inside this peripheral from secure operations is linked to the non-secure side. But again, I'm just underlying that this is not necessarily, or actually this is not a primary use case. But there is a workaround of that. It has some performance issues. You might do a lot of resetting and clearing of the peripheral and generally of every resource that you want to runtimely bounce between the two states. But TrustZone enables you to do that, and then it's the responsibility of the developer to do this.
Okay, thank you. I encourage you to continue discussion in the discussion zone, and thank you very much for presentation. What is the best 3 questions? Okay, we have 2 shots.
It's very hard to decide. I can leave it up to you. There was many questions here. All questions were good. I like quite a few of those.
Okay, so guys, if you feel that you ask the good question, please come in here for 2 shots. Thank you very much, Ioannis, for presentation. Thank you.
Welcome.
I will continue in less than 10 in 5.